Hello, this is A Squared at mathandstuff.com. Today we're going to review a video. I've gone to the video link at the bottom of the page. The sketch pad we are going to be using was written by me, but the Geometer sketch pad may be downloaded at no cost from KeyPress. Here's a link for it. As with other videos, all the material used on the video is linked here for you to use. We're going to the web page, and the first picture you see is from the definition in the dictionary. And that's the definition. We're now going to not bother with that. We're going to use the sketchpad. The sketchpad has the definition, and above all else, you should know that abasement is a cumulative function. Normally, functions are f of x. Their derivatives are f prime of x. And the rates of change are the second derivative, f double prime. But it is also true that the second derivative is the derivative of the first derivative, is the derivative of the function, and the function is a derivative of a cumulative function. Most people seem to be calling it capital F. In the notation introduced recently, grouped as the nth derivatives, the Absement function, or capital F of x, is listed in their list as f negative 1. So it's not f prime, it's f to the negative 1 of x. Other links are positioned on the left-hand side. You can go to the definition in Math and Stuff. You can go to Wikipedia. You can go to other sketch pads at Math and Stuff, or you can go to Calculus Stuff. Another thing it's important to know is all the derivatives in this sketch pad are fake. They're all using the slope of a very tight secant. Time, or the x value, can be moved. What that permits one to do is isolate the time and isolate the function value. In this case, we're using distance or displacement. And you just roll it, scroll it, drag it, and the values are available. That permits one to look at the definition of a derivative from a more concrete point of view than is available in a textbook. One might see a picture like this in a textbook, but because it's on a sketch pad, things can be moved. So if you wish the derivative at this x value, position the x value where you wish it. Then, since the limit of the slope of the secant as h goes to 0 is the tangent, the slope of the tangent, the limit of the slope of the secant, the limit of the difference quotient is your derivative. Can't do that on a piece of paper. I've laid it out here to include not just the variable value, but the function value and the derivative. It's clear that that's a positive slope. That's an even steeper positive. That's a negative slope. I believe the tangent line makes it easier to see the slope. I'm going to try and make the slope 0. That's about as close as I can get to 0. I've introduced an additional segment here. In red is the acceleration. If the displacement is your function, then its first derivative is the velocity, and that's this green tangent line here. And the acceleration is this red. So what's really nice with this picture is you can see that the tangent is the slope of the tangent, so the derivative is changing. It's still positive. The change in the change in the velocity is negative. Still negative, still negative, still negative. See how it has a negative slope? Still negative, still negative, still negative, still negative, still negative. Still negative, still negative, still negative, still negative. Notice when we peek out here, our velocity is 0. That's our tangent line. That's our max. But more interesting, now we see that the slope is negative. The second derivative is negative. Notice that the slope remains negative, but the second derivative, you can now see it, is becoming less and less negative. And as you approach a value of 0 for the second derivative, there, oh, we just about had it. There you go. That gives you the inflection point. You can see by this line and by that number that the second derivative is now 0. And as I continue to the right, the second derivative has a positive slope. The concavity has changed. It's no longer in the concave down region. It's now in the concave up region. Another picture we have permits one to use emojis, little stickers. So if you want to do a little sticker here, oh, let's go. Let's look at this point, this value of t. That's the function value given. That's the slope, it's positive. That's the derivative, it's negative. I'm just going to mark the slope as a positive. I'm going to mark the derivative of the second derivative as a negative. So it's going down, concave down at that point. If I slide it over, that's about as close as I can get to 0 for the slope. It's still concave down. It's now a negative slope. Still concave down. Watch the second derivative. Okay, we switched from here to here. That's about as close as I can get. The second derivative is 0. That's an inflection point. The slope still happens to be negative. And we could go on from there. We could also look at a tracing feature. When I take, okay, I'm going to just, Make it a little more visible. Let's go with the first derivative. The first derivative, the derivative of the sine, should be the cosine. Clearly, that's the cosine. Let's just move this over. Okay, well, what's the derivative of the cosine? That would be the purple one, the second derivative. The derivative of the cosine is the negative sine. Let's go for a third derivative. The derivative of the negative sine should be the negative cosine. Find orange. There we go. That's a negative cosine. And the derivative of the negative cosine, nope, should be the sine. Let's see if we get it. Find the red. Sometimes I pull the wrong red one. There we go. Sine function. So what I've attempted to show you is the cyclic nature of the sine and cosine derivatives and antiderivatives. In building for the antiderivatives, you need Riemann sums, Riemann boxes. Here's a box. I've placed these boxes so that you're using a left-hand sum. And I can move the boxes. And if I were good, I could adjust the height. But I don't do this very successfully all the time. That's the best I can do. And if you wanted a right-hand sum, the picture's already drawn for you. In this case, to find the areas under the curve, I'm only using left-hand sums. That's what I'm using for the rest of the sketch pad. I have permitted adjusting the A and B, the interval, the upper and lower limits of integration with a box rather than sliding it. So let's go from 2. Maybe let's go to 6. There's the curve I want. The area I'm looking at is between the function and the x-axis. It's negative. You can see it's much more negative, but we also have the ability to change a new function. Let's just make this, let's make it a 4. So now what we're looking at is these pieces, and it got even more negative. And let's just one more. All right, let's make this 0. Let's make this so it's always positive about 2. There we go. A lot smaller area, but you can play with 2 functions. Here's I think, more graphic picture of the fact that you're actually finding an area. The difference between these two is the number of partitions. To do a normal distribution, I could click on that. I'm not going to bother. you can click on it. It'll take you to another spreadsheet. Absement is a cumulative function, just as the cumulative probability distribution is. Here we have a line graphed. Its antiderivative is a parabola. And I'm just going to change this a little bit. Oh, let's make it a 4x. No, a 0.5x. Better, you can see the shape here. The more parabolic. Let's make this down to let's make it -20. That's too much for me to use. No, I can do it that way. And let's see if I can just adjust this. Okay, it's clear that it's a parabola, but it's really supposed to be at 0, 0. So that's where the plus C comes in. Let's add 50. That should pull it up a bit. Not enough, but does pull it up a bit. Let's pull it up 80. Let's pull it up 90. Almost there. Let's make it 95. That's probably as close as I'm going to get. I'm not going to get it perfect because I'm not using an antiderivative. All I'm using is Riemann sums to approximate the antiderivative. And as soon as I change the A and the B, and I change the C, the arithmetic of the computation changes, so I can't always get it perfect. It's not a surprise. I've given you, in this one, a parabola. The antiderivative of a parabola is a cubic. I think you can see the cubic. The concave down parabola, concave down, well, not concave down, but reflected cubic. And you've seen why the plus C is important. Last two ideas. Arc functions are inverse of trig functions. And if I go slide it out of the domain of the arc function, I will not get the points to end up in segments. But you can see that the arc sine is the inverse of the sine as it's reflected over y is equal to x. So why in the world put it in this sketchpad? This is the reason. For the arc function, on a calculator, you can press an arc function button. Before the calculator and for mathematics, you need a real live function. Now, these were generated, and I could give you the link. Don't need that, though. But this is the function that's the derivative of the arc function. The derivative of the arc function is the reciprocal of the derivative of the sine function at the reflected point. We go back to here. Doesn't look like it matches. Let's make it match better. Again, we're using left-hand boxes. So I got to make sure that I don't use -1 because it won't be in the domain because I'm using the boxes. So let's go with -0.99. Okay, we can see it's got a nice curvature. It doesn't look like it matches. I'm going to go with pi over 2, 1.57. And I'm subtracting 1.57. Let's see if I can get them to where I need to be. Yep. Now, just to prove it to you, let's graph the arc function. Bingo. Right on target. That's how you use the Sketchpad that you can download for free. This is what I suggest. Go with the most basic, the most concrete as an introduction. Summarize in the abstract. Use the mother tongue. In other words, speak the language that your students are speaking. Use multiple modalities. Repeat as much as you can in different languages. If you're going to review, don't just throw computation of symbols at students. Let them see it in a picture, as in you want to show them the work. If you have all the work laying there, ready for viewing, it's easier than if you have to write it out. When you do begin mentioning the words velocity, acceleration, and derivative, and second derivative, when you present the definition of slope, definition of derivative, and the slope of the secant and slope of the tangent, at that time, also mention the word absement when you introduce displacement, velocity, and acceleration. Just call it total displacement. Don't worry about an antiderivative. They don't need that. They need cumulative function, and it's much more important than the word abasement, absement. Again, cumulative function. Here's the notation I suggest. And notice that all I'm doing is stating it in terms of derivatives, with this being cumulative. So the velocity is the cumulative. The velocity over time is the cumulative displacement. Cumulative is what you should reinforce.